Hello everyone, this is going to be another thermo video, and in this video I'm going to be going over an example problem mainly dealing with refrigeration cycles. So the problem reads, a refrigerator operates at steady state with a coefficient of performance of 4.5 and a power input of 0.8 kilowatts. Energy is rejected from the refrigerator to the surroundings at 20 degrees Celsius by heat transfer from metal coils attached to the back. Find A, the rate of energy rejected in kilowatts, B, the lowest theoretical temperature inside the refrigerator in Kelvin. Okay, so to start off, what I like to do is I like to write out what we're given in this problem and what we have to find. So I'm just going to underline what we're finding here. So A and B right there. And in terms of our givens, so we know the coefficient of performance is 4.5. We also know that the power input is 0.8 kilowatts. So we know that that's W dot in is 0.8 kilowatts. We also know the temperature of the surroundings. So T surroundings, 20 degrees Celsius. And let's just convert that right now to Kelvin. So we get 293.15 Kelvin. Okay, so after we write our givens, I also like to write our assumptions. So what assumptions can we make with this problem? So for the first assumption, you can say this is steady state. Okay, because it mainly tells us that here. And then in this case, we can call, so knowing that this is a cycle, we know that there's going to be a hot and a cold reservoir. So we can call the hot reservoir our surrounding atmosphere. And similarly, we can call the cold reservoir the interior of a refrigerator. Okay, so from here, I also like to draw a schematic. So I'm going to switch colors. Okay, so I'm just going to draw the cycle here that we're dealing with. Okay, so because this is a refrigeration cycle, we know that the goal of a refrigerator is to get rid of heat, because it wants to stay cold, right? So if we treat our T cold, which is the cold reservoir, if we treat that as the interior of the refrigerator, then we can call this QL. So that's the Q that's leaving. And then that means that QH would be the Q entering the hot reservoir. And in order for this to happen, so since it is opposite of the natural flow of heat, we know in order for this to happen, or the only way for this to happen, is to input some power. So we have a W dot in entering our system. All right, so with that, now I'll begin to solve this problem. So let's do this here. So solution. Okay, so to start off, since we're given the coefficient of performance of a refrigerator, let's write the equation for that down. So we know that the COP for a refrigerator is So COP in general is just our desired output as our numerator divided by the work in. So since the COP for a refrigerator, our desired output is this QL, it would be QL over W in. All right, and we know this is 4.5, it's given. And we know W in, of course, is also given 0.8 kilowatts. So if I solve, we get that QL dot. It's 3.6 kilowatts. All right. And from here, so notice how similar to the other video, we can treat this as a system. So if we go ahead and do an energy balance, we get W in dot entering plus QL entering the system is equal to QH, which is leaving the system. So entering equals the leaving, right? And we know all these values. So since we're trying to find the rate of energy rejected, we know that the Q rejected is our QH in this case because it's rejected from our system here. Since this is our system, this is the one leaving our system, or the only one leaving our system. So this is the same as Q rejected. Okay, so with that, if we put in our numbers, 0.8 kilowatts for W in, QL is 3.6 kilowatts. We get a value of QH, or Q rejected in this case, of 4.4 kilowatts. All right, so this is part A. So now looking at part B. So we're trying to find the lowest theoretical temperature inside the refrigerator. So for part B, so let's just write what we know so far. So we know T surroundings is 20 degrees Celsius. So in our case here, we already assume that the surroundings is the hot reservoir. So that means that T surroundings is equal to TH in our case, which we know is 20 degrees Celsius, or of course 293.15 Kelvin. So with that, in order to find the lowest TL for a given coefficient of performance, this means this will happen if the refrigerator is reversible. So in order to get the lowest theoretical temperature, we have to make it a reversible system. So assuming it is reversible in that case, then we know the coefficient of performance is still 4.5. And for a reversible refrigerator, the equation is 1 over TH divided by TL minus 1. Okay, so now if we just plug in our values, 4.5, so if we go ahead and solve for TL in this case, we get TL of a value that is approximately 239.85, and that's in Kelvin. All right, so this is the answer to part B. And of course, TL, that's the same as the temperature inside the refrigerator. Again, because this T cold is TL, I should have written. So since T cold is the temperature inside the refrigerator, and that is equal to TL, since the interior of the refrigerator is our cold reservoir, that's why TL is equal to the temperature inside the refrigerator. Alright, so I hope you guys enjoyed this video. If you want another example, I will be posting one in the following videos with the same concept. Alright.